Welcome everyone. Thank you for joining us today. We are happy to have you here for the webinar on top-load testing, ensuring package integrity from production to transport. Before we dive in, there are a couple of housekeeping notes I would like to share with you. Today's session is brought to you by Mecmesin, a proud member of the Physical Properties Tester Group, a global leader in physical properties testing. The PPT Group is also home to other amazing brands, including Lensman, James Hill, and Aluris. Together, we offer innovative solutions for testing tensile and compressed strength, torque, textiles, and the effects of shock and vibration, among other parameters. For more details about the group or any of our brands, please visit the website. We will also share a link to our events page in the chat box for your convenience. Now focus on Mecmesin. We have established technology labs across the US, UK, and Asia dedicated to supporting our customers with education, proof of concept, and demonstration testing. If you have any specific needs in physical properties testing, our global team is at your disposal to provide the assistance you require. Let's introduce you to the team for today's webinar. So Moses of Russia will be our presenter. I'm Laura Calazans, one of the coordinators. Additionally, we have support staff and partners stationed across Asia, Africa, Europe, and the Americas, ensuring that no matter where you are, we have a local expert ready to support you. We are aiming for a dynamic and engaging webinar, so we encourage your participation through questions. Feel free to submit any questions that you have at any point during the webinar using the question box. We will address them at the Q&A session at the end. This webinar is being recorded for your convenience. The recording will be sent to your email address you registered with, allowing you to share it with colleagues and revisit as many times as you need. Now, without further ado, I'll hand it over to Moses so we can start.
Thanks, Lara, and thanks everybody for making our webinar today. So we'll be looking at a few things on top-load testing. I'm hoping to cover as much ground as I can. And the reason for that is usually top-load testing is such a broad topic because of the different types of samples that are available for top-load testing. Today, however, we'll focus more on blow-molded plastic containers because that forms the core or the majority of the top-load samples that are usually tested. But the principle still remains the same, whether you're testing plastics or cardboard, corrugated cardboard, or metals or aluminum, or whatever type of container you need to apply compressive forces to. So our agenda today is quite simple. We'll have a quick overview of what compression testing is all about in physical testing. And then we'll look at the importance of top-load testing. We'll also take a quick brief look at some of the industries where you'll encounter top-load testing. We'll look at some of the primary top-load testing applications on exactly how samples are tested under that broader umbrella of top-load testing. Next thing, we'll look at selecting the ideal fixtures and testers. And then we will have a live demonstration of the three major principles in top-load testing. That way, at least you can kind of connect the dots on everything we're about to discuss, so you can also visually see what they look like in real time. And then finally, we'll look at some of the factors that affect consistency and repeatability in your testing environment. So for starters, compression testing essentially is a simple test that provides integrity and safety of materials, components, and products. What you're looking for is just checking to make sure these samples actually meet certain standards. It usually involves applying a uniaxial force to measure the performance of a test specimen under compressive load, either up to the point of yielding or breaking, or sometimes if it's 100% or non-destructive test, just to see how the sample actually reacts under a compressive load. The sample under test may simply be a test specimen of raw material or an actual finished product, and I will discuss that a little bit further later. Test samples are usually compressed with a plate or a probe, and the load is applied at a constant rate of speed. Data collected can be plotted on a graph showing a force versus extension or displacement or deflection in a typical force testing application, or on a stress versus strain curve for more materials testing. You can also show things like modulus and so on. Essentially, compression testing is performed with compression plates, probes, and fixtures, but mostly with compression plates, and we'll discuss that as well in the section where we discuss the types of ideal fixtures to use in these types of tests. And as we discussed previously, the test may be destructive or non-destructive. All right, so what is top load testing? Again, we're using the universally known term of top load testing, but you'll also encounter that described differently as column crush or axial force resistance, compression test, burst test, all kinds of different descriptions, but it's essentially just a simple test performed mainly on blow molded, thermoformed, or injection molded plastic containers. Now that's what the definition says, but as I mentioned, the key is simply measuring the compressive strength of these containers to ensure that they do not deform or break when subjected to axial forces during the processes of filling, closure, storage, and transport from factory floor to shelf. It's a reliable method for measuring the integrity of containers that are used for a variety of products and purposes, including plastic bottles, cardboard boxes, metal cans, shampoo bottles, yogurt containers, food trays, crates, foam cups, paper cups. There are all kinds of different samples that can be tested under that general umbrella of top load testing. So why is it important? Again, usually, if you're a company that's been thermoforming plastics for 40 years, you trust your processes and you say, oh, maybe we don't need top load testing. Only until, your important, expensive beverages collapse under the weight of boxes that are stacked 5 high, 10 high, again, either in storage or during transport or when it gets to the store. And that could mean something for the bottom line. So at almost every stage of production in research and development, where we're determining the product viability, strengths, and weaknesses, in quality control, where you're establishing product standards for quality and safety, or during production, where you're maintaining those established product standards for quality and safety, you need to perform some types of top load testing. And then in cases where, let's say, you're simply a bottler or a beverage producer and you're getting supplies of plastic samples and they've given you these top load values, if you're looking to verify that those materials actually meet your quality and safety standards, you can also perform top load testing to make sure when producer A sends you the products and they give you values, you can actually check your test results against those values to make sure they actually do meet those testing standards. So there's several different industries where you'll find top load testing: food and beverage, medical and pharmaceutical, in automotive and aerospace, in paper and plastic, in cosmetics, in manufacturing. And among these, you'll have different types. I just didn't have enough space here to capture every image, but you get the idea, whether it's a gas can or windshield washer fluid container or motor oil or medication container, or your favorite beverage. And as I mentioned, whether it's glass or paper or plastic or metal, some types of top load testing is performed to make sure they do meet those quality and safety test standards. So there are 3 main top load testing applications. The first procedure, which is the most common, is when in a tester you run at a constant rate of speed, compress the sample to a known displacement, usually 1/4 of an inch or 6 millimeters, and then calculate what your top load is. In this case, it's going to be the peak or the maximum force. All containers are subjected to the exact same test. That way, if you grabbed a handful of containers off the production floor, put them in and ran them to the same testing parameters, if they're failing at your 1/4 inches or 6 millimeter displacement, then hey, it's too much, there's something going on, the bottles are too thin, or If you've seen higher than usual forces, then you can go back and say, you know what, these bottles are coming out a little heavier than usual. In each one of these instances, it means something to the bottom line. Too much plastic means something to the bottom line. Too little plastic means something to that bottom line. So you just need to have your ideal sample thickness, sample weight, and those are some of the critical objectives of a top load test. The second test is where, similar to the first test where you run into a known deflection or displacement, this time you're applying a known force. So in this case, where let's say as a beverage producer A, you want to verify that the plastic bottles that have been supplied you by supplier A actually meets a certain axial force standard. So you say, oh, you can put 200 pounds on this bottle and it will still be fine. So in this case, you run at a constant rate of speed, apply a known compressive force to the sample, and then calculate the peak deflection. So you'd say, if you apply 200 pounds, it should only deflect about a quarter of an inch, or it should deflect about 10 millimeters, or it should deflect about 2 millimeters. So when you do that and it's deflecting more, or it's not deflecting at all, you can then revisit the too much plastic, too little plastic scenario and figure out what's going on. And then finally, that third procedure is where you run at a constant rate of speed until the sample fails. So depending on how the sample is designed, if it's a regular bottle, sometimes also as part of the R&D process, you're just looking to see the weakest point of the sample. If that sample fails, where is it most likely to fail? Is it at the neck? Is it in the middle? Is it on the bottom? Is it going to fold in? So those are all ways of gathering enough data that informs your production processes to make them obviously better in order to meet your quality and safety standards. So these are the three main tests that you'll encounter. Now, in any given testing environment, you can adopt one or two or all of the above, especially when you're looking to gather as much data as possible about your product. So in that third instance, once the sample fails, you want to know first and foremost, what was the maximum force you acquired before the sample failed, and then what was the deflection at that maximum force before the sample failed. So once we get to the live demo here, hopefully we'll be able to show you all three types of tests and what they actually look like in real time. All right, choosing the ideal tester. One of the questions that we usually encounter is, can I just, use a force gauge and just push down and read a value? Yes, you can, but the integrity of your brand and your brand name is actually at stake. Are we going to pick the guy with the biggest forearms and have them do this? It's okay if it's some, really small operation and you're not looking to make the investment, or, again, I never want to use the term quality is not a big deal. Of course, quality is always a big deal, but you could get away with that. However, if you had 10 different people, are they likely to get 10 different results on a handheld gauge? More than likely, yes. So in that case, your whole concept of gathering data becomes moot. You're not really getting usable data that can actually inform your manufacturing or production processes. So in that case, a good option is using a motorized force tester, attaching that force gauge, which actually measures your compressive force. Now, the advantage of that motorized tester is the two critical factors that users usually would have to guess, which is how fast they're pushing down and how far they need to go, is answered using a motorized tester. So you can program it to run at a known speed of, say, 10 inches per minute and run to that known displacement of, say, 10 millimeters or 6 millimeters or a quarter of an inch. And then obviously that gauge will recognize and register whatever the peak compressive loads are. Now, this is usually good if you're looking to perform the test number one, where you're compressing to a known deflection and then simply measuring whatever the peak load or the top load is. In other instances where you want to apply a specific load and then measure what the peak deflection is, you're at a bit of a loss, because especially in cases where you have different sizes of samples that require different loads, you'll always have to constantly go in and program. And again, the more you're asking operators to be involved in the processes, the more error you're introducing into your testing environment. So in that case, your best method is your software-driven tester, where each test is configured specifically to the sample that's being tested in cases of whether you're measuring displacement, whether you're measuring top load, whether you're measuring both. You'll have each test uniquely configured. So all the operator has to do essentially is just call up the test, put a bottle in or sample in, and hit the start button. The rest is all taken care of. And then when it comes to reporting, you have different options for exporting your data to Excel or to a CSV file, or to generating PDF test reports. And then obviously you can also make different modifications to the test depending on what your needs are through additional calculations and so on. So essentially, in a software-driven testing environment, you have some variability and versatility in how you approach your tests, especially in cases where you'd like to apply all three test types, whether you're running to a displacement measuring force, or applying a specific force measuring deflection, or just running until sample failure and then measuring both peak force and peak displacement. You can configure all three tests easy. Just call them up, put the sample in, hit start. So it saves time. It removes any guesswork, which essentially helps you establish a more consistent and repeatable testing environment. So these are the different approaches that we recommend, preferably a software-driven tester. So once you've selected your tester, the next question is, how do you choose the ideal fixtures? Now, most of the time, there are a couple determining factors. One, the type of sample being tested. Is it plastic? Is it metal? Is it aluminum? Is it paper or cardboard, corrugated cardboard? That's the first part. Next thing is the sample size. You know, is it 50 millimeters in diameter in the container opening? Is it 100 millimeters in diameter in the container opening? Is it square? Is it round? Is it rectangular? So those are all the different factors that go into selecting the ideal compression plates to use. And then finally, also, there are instances where you'd like to use a vented compression plate on an empty container in order not to build up air in the container. So yeah, in a finished product where the beverage has already been filled and it's capped, you can use a regular compression plate. And where it's an empty bottle, you do want to use a vented compression plate, which is essentially a compression plate with either slots in it, as you see there in that top row on the left, or you just have a couple of holes to essentially let the air out, so you're not building pressure, because that it tends to spike the compressive forces and might not give you a true top load value. So again, different sizes and materials. And then they come in different shapes: round, square, rectangular, and as I mentioned, they're going to be either vented or non-vented. You can also have samples that may have slippery surfaces, and those are instances where you would use rubber-faced compression to kind of prevent the plates from slipping. And then also in instances where you have containers that are not evenly surfaced, you might use a self-leveling compression plate to always make sure that the compression plate is sitting flat on the container, no matter how uneven the surface is. So these are the types of compression plates that you might encounter in selecting the ideal fixtures for your top load testing application. And with that, I will go over to our live testing here and then walk through the 3 different tests that we discussed. So if you bear with me just a second. So first, this is what the test looks like. So test is being run on a software-driven OmniTest 2.5. We have an oversized base plate to accommodate the different sizes of containers we're testing. Now, again, for purposes of our webinar, we're essentially just going to look at different sizes of bottles and how they react under compressive load. In that process, we'll run a couple, 2 tests where we're compressing to a known displacement, measuring the peak load, a couple more tests where we're applying a specific force and then measuring the deflection, and then that final test where we're compressing until the sample fails to see, you know, where the sample actually fails. So the deflection at failure and then the maximum force at failure. So those are the types of tests that we're going to run today. I would also like to share the software screen so you can see what this test looks like. Now, the first test we're going to run is a top load test. We're calling it RTD here, which is essentially run to displacement. It's a very simple process. When you look at the test, you're essentially looking at an operation that says first run to a touch, run to a displacement, return home. Again, for purposes of our demo, we're keeping all of our measurement units in newtons and millimeters. There are options for testing in your preferred units of measurement, kilograms of force, ounces of force, pounds of force, and so on. Displacement units can be inches, millimeters, microns, what have you. And then in the test results, we're simply just calculating the maximum load on this particular test as we're running to a specific displacement. As I mentioned previously, in your software-driven testing environment, you have options for exporting data to Excel, exporting data to a CSV file, exporting data to a PDF to create a report, and so on. So once the test is configured, all the operator has to do when they log in, and there are different user account controls and permissions for what users can and cannot do. For instance, can they delete tests? Can they make modifications to the test program? And with it, also an audit or event recorder that records everything a user does in the software for audit trail purposes and for auditing purposes. So the QC manager knows what everyone is doing. So all the user does when they log in, simply click on that, and it is going to open your live test screen. A couple of things I'm going to do here. Just choose a better contrast for the traces so we can see that better. So first thing I'll do here is set a home position, because we're asking the crosshead to return home so we can put the second sample in. So obviously we do want it to return to a known home position. And at this time, all the operator has to do, as you can see here, sample's ready, just hit start. So what we're asking it to do is come down, find the surface of the bottle, the top, touch the top, and then compress to 6 millimeters of displacement. So that's our test. And then back off. That's our first test. I'm going to run the second test here, and then we'll kind of look at the test results and what they look like. So just swapped containers and start. Again, it's going to look down. So the graph will give you a live graphical representation of the test. Now, there are also options in the software that essentially allows you to measure the height of the container by setting an absolute zero position. So the way we do that is just bring the upper plate to touch the base plate, create a home position for all the different sizes. So when compression plate comes down and touches the surface of the bottle, it will measure the height of the container if that's also an information that you'd like to include in your data. So these are two tests overlaid. And as you can see here, the events are happening almost around the same points for each sample. So from the graph screen, if you toggle over to your test results, there are a few things we can see here. That first test, the top load was about 434 newtons. If you click on that little icon, so listen, this is the highest point of the test where I recognized it. Now, this is only because we're compressing to a 6 millimeter displacement. In certain applications, the third application, which we will look at, if we wanted to stop the test at that first instance where it reached the peak and just stopped, we could have stopped the test, and you'll see that once we get to it. So this is the first test. It's capturing the highest peak in the test right about there. Now, there are, again, this is one of the advantages of your software-driven tester. This is the second test that's also capturing that right there. So if you said, yeah, you know what if I wanted to capture that? You could. All you have to do is, as you see here, that peak is happening before the 4 millimeter mark. So we can say, capture that peak between 0 and 4 millimeters, and then we should be able to do that. And you can do that in real time simply by clicking anywhere on that screen. Sorry, here we go. And then we'll say we want to see that between 0 and 4. And then go back. So now if you go in, you see it captures that right there. And then in that second test, it's capturing that right about there. But again, again, for demonstration purposes, there are also ways to capture a first peak, second peak. It's a calculation in the software that you can use, especially if you get multiple peaks in the test. All right. So this is what a typical run to displacement test looks like. If you want it to run to a specific load, bear with me here while the test loads. All right. So this is our run to load test. Again, the only modification here is instead of running to a displacement, we're applying a known force of 100 newtons and then seeing how much that sample deflects. So again, we'll go straight to the live test, and then we'll change the contrast just a little bit. And I'm going to swap these containers out, put different containers in there. All right, here we are. Excellent. So all we're going to do here, again, set our home position and then start the test. It's only going to apply 100 newtons to the sample after that initial touch. So touch. Oh, that's interesting. That wasn't much at all. Let's see. It did not see it. Bear with me just a second. It wouldn't be a real test unless one of these failed, right? So let's try that again, if we could. Oh, wow. Okay. Something wrong there with our little test. We will find out what. All right. So bear with me. We'll go back and do a quick reconfiguration of our test. I promise it did work before our. Okay. So let's see. Edit. Take a quick look at what is going on. So we did ask it to apply a load of 100 newtons. So let's see. I think it's on. Oh, you know what? Let's try again. I think I see why. I see exactly why. We did not specify a speed. Let's do that. 50 millimeters per minute. Of course, makes perfect sense. So flexibility of your software driven, anytime you recognize something is off, within seconds you can go in, make whatever changes are required, and then third time, I promise, will be the charm. There we go. That's our touch. And that's 100 newtons. Perfect. All right. Once again, I'm going to run a second test so we can, I'm going to do this on a different container as well, so we can kind of have a quick idea of what, especially when you're doing a comparative analysis, you can kind of mix and match what your containers look like. So again, set a home position for this because it's slightly a different home position. Change our contrast one more time and run. Let's touch. Okay. So now, excellent. So that's sample one. Now there are annotations here. We'll say this was the clear. So that way anybody looking at the test will say, oh, sample one was the clear bottle. Sample two, we'll just call this green for now. And save that. Okay. So in your test results, we're trying to see when we apply 100 newtons of force, how much does the sample deflect? In the clear bottle, it only deflected 1.4. millimeters, and then in the second bottle it deflected 1.9. Now at 1.9. Now on the surface you can clearly tell one of these bottles is softer than the other. One's a little firm, so the more rigid the sample, the less deflection you're going to see, and obviously the softer the sample, the more deflection you're going to see. So this is how much it deflected on that first sample, and then this is how much it deflected on that second sample. Now in any of these test results, whether you're capturing force or top load or you're capturing deflection, there are also ways to apply pass or fail criteria to your tests. So let's say, hey, on these bottles, product A, when we apply 100 newtons of force, we only want to see, let's say, between, we want to see between 1.3 and 2 millimeters of deflection. Anything above that is, again, anything below your minimum, too soft, too rigid. Anything above your maximum is too soft. So you can create that pass or fail. Now, one of the advantages here is sometimes you only need to meet a minimum threshold. So as long as we see a 1.5, we're good. In that case, you can just simply disable the max and just meet that minimum and you're good, everything's gonna pass. Or you can say, you know what, we don't want that minimum. However, if we exceed a certain maximum, that would indicate the bottle is too soft and we need to revisit what's going on. So in that case, if as long as it's below your maximum, everything is a pass. However, if it goes above your max, we're going to say it's too soft. Or in most instances, you'd create a range of your pass or fail criteria. So once you create that range, as you can see here, that 1.4 is failing and that 1.9 is passing. And this happens in real time as soon as the sample, the test is completed. So if I went back to the graph and just simply test it again, now, not always a bright idea to retest the already tested sample, but I just wanted to quickly show you how you can see that pass or fail result in real time as soon as the test is completed. All right, so end of the test. Now, when you go to the results, as you can see here, that's another pass because it falls within, so it was 19.08 millimeters, 19.03, that's within your pass or fail criteria. It immediately gives you that check mark to indicate, you know what, yeah, this was a good test. So this is what a typical run to load test looks like, where you're looking to measure the container firmness or the rigidity of the container, where you're measuring just the deflection. All right, and then in that third and final test, exit, I'm just going to save all of these. I will just take a quick look at the test configuration, make sure we have everything set as we should. So this, in the operations, this is going to run until the sample fails at a speed of 250 millimeters per minute. And then in our test result, we want to measure both the peak top load and the peak deflection. So that's all there is to that test. Again, similar to the other two, but this time we're going to run until the sample fails. So I will get that started while I swap samples here. Okay, this is test number 3. So I have RTF there as in run to failure. And if you give me a few seconds, I'll set the samples up. Okay, so we're going to have, reason I reserved the last 2 samples is they're pretty much the same. So once again, if you bear with me, I'll bring this down here to right about there so we don't have to sit and wait and wait and wait. Okay, and exit. Okay, excellent. Now we're going to set our home position and then start our test. So once again, it's going to come down, touch the top of the container, and this time it's going to keep going. It's not going into a known deflection or force. It's just going to keep going until it sees a failure. There we go. That's the failure condition, and then it's just going to back up. So that's test number 1. This is the second sample. All right, go start. I'm going to run test number 2. Touch. All right. And sample failed. You love really friendly containers that will give you both an audible and a visual on when the sample actually fails. So in this case, we had two calculations there. We're looking at maximum force, which is what was the highest force before that sample buckled. It's about 378 newtons. And then on that second one, it was 378, second one was 374. And then your peak deflection, how far did it deflect, was 4.172 millimeters. And on the second one, it was 4.273. So this is really tight. That tells you there's some consistency, even though, yes, I know we're only testing two samples, but this is the third type of test that you usually would do in R&D if you're looking to gather as much information as possible in your testing application. So these are the three types of tests that you usually would encounter in top-load testing. Now, there are other different test parameters that we could be looking for depending on the type of sample, where you'd say, oh, you know what, compress this to there, and I want to know what the value of the load was at 50%, 25%, and so on. But again, this is one of the reasons that software-driven testers are your friend, because that way, regardless of what the simplicity or the complexity of the test, you have different tools you can use to gather as much data about your product as possible using the inbuilt calculations. Or sometimes you can even build a really wild calculation using the formula feature in the testing software. So this is, again, test number 3. And now we'll look at some of the factors that actually affect consistency and repeatability in your testing environment. All right. So all things being equal, you expect to put samples in, call up test A, run a test, and out of your 10 samples, 9 are passing with flying colors. So that's your ideal happy testing environment. You and I both know that doesn't always happen. And so if anything goes wrong, or if the data is all over the place, what could possibly be the problem? And we've laid out several factors you would be looking at if you had to use a checklist. The first thing is, obviously, you need to determine the objective of the test. What are we looking for? Are we running to a load and then measuring our deflection? Are we running to a displacement, measuring the top load? Are we running until the sample fails? So just like with anything, the objective is critical, right? You need to know, why are you even testing? That's critical. And then once you've determined that, the next thing is, how do you get there from here? That's a two-part answer to this. First, it's the actual testing procedure. Are we testing to an ASTM standard, an ISO standard, or do we have our own internal standard? And if so, what's the equipment required to go from A to B, or from start to finish in the testing application? So we go back to the ideal tester and the ideal fixtures. So imagine having a square container and a round compression plate with some overhang. Obviously, you're not looking at consistent results. So those are some of the factors that go into it. The ideal fixtures are just as important as either the objective or the test procedure itself. And next thing is, are there standard operating procedures being followed? Are all the operators following the same rules? One, nobody's touching the containers with greasy hands. We need to place these containers in specific spots. They're not offloaded and so on. Everyone follows the same rules for each sample tested. And again, that enhances your testing environment. And then have the appropriate testing requirements been established. So for instance, what we just did here is unconventional. It was only for purposes of our webinar. Testing different sizes of samples altogether makes it a little difficult for any data analysis. Ideally, you have 10 samples of product A, 10 samples of product B, 10 samples of product C, and you test all of them together. So if there are any outliers, or you can easily identify and say, okay, out of these 10 samples, 9 are passing. There was just the kind of the one which either might have shifted or something wrong. That's great. If the reverse is true and you're testing 10 samples and only one of them is passing, then we have a problem, right? So you might have to go back and figure out what's happening. Is there something happening on the line? Is our production process putting too little plastic, too much plastic? Is that why we're seeing higher values than usual? Is that why we're seeing lower values than usual? But all in all, once all of these boxes have been checked on your checklist, you almost kind of, certainty is a different matter, but you almost certainly guarantee a consistent and repeatable testing environment, or at least you give yourself the chance to pinpoint where any errors might be coming from, whether it's in the objective of the test, whether it's in the selection of the equipment and the fixtures, whether it's in the actual testing procedure, whether it's in exactly what the pass-fail criteria is for the different samples you're testing. You're not mixing and matching. Or is it actually coming from the production process itself? So having the right tools, following the same right procedure helps you to pinpoint where any errors might arise in your testing environment. And with that, I'd like to hand over to my colleague, Laura, for any questions. Over to you, Laura.
Thank you, Moses. Let's have a moment to collect our thoughts. And if anybody has any questions and you have not sent it to us, please use the questions box. And let me look at some questions here for you, Moses. 1 second.
Sure.
Okay. First one, how do you determine the deflection rate to use?
That's excellent. So excellent question. So the deflection rate to use is, it's almost an unwritten industry standard of the 1/4 inch deflection. So again, you can do the correct conversion if you're testing in millimeters or a different measuring unit. But for the most part, a 1/4 inch deflection will kind of give you an idea. Again, that's what is the recommended. But in your own unique testing environment, you might need to run it to 1/2 inch to 1 inch. Especially in R&D, if you like to see, you want to push the container as far as you can to see what you find, either in terms of your max deflection or your max load. So again, what we've seen universally used is the 1/4 inch deflection, or 6 millimeters. Back to you, Laura.
All right, thank you. We have a couple more for you, Moses. So the next one is, what is the difference between using a vented or a non-vented compression plate?
Excellent question. So we recommend the vented compression plates for empty containers. Again, the key here is using a non-vented kind of seals the container while it's under compressive load, so it kind of builds up pressure, and it might create or spike your compressive forces and not give you true compression values or top load values. So using the vented essentially allows you to let the air out and just compress the material itself. In cases where, let's say, producer A of plastic bottles sends it to beverage producer B, and they fill it and cap it, then you can use a non-vented compression plate to just, compress it to either look for one of the three things that we've discussed previously. So filled containers, non-vented; empty containers, vented. Back to you, Laura.
So the next one is, do you use a percent yield to determine when the bottles fails during RTF, and how is that determined?
So this is a more complex question, Maddie. And the reason for that is, in terms of just physical testing, you're usually using either the point of deformation, the point of failure, in terms of the max load at failure or the max deflection at failure. Again, this kind of calls up the beauty of using software-driven testers, because there is a yield calculation in the software that will allow you to calculate the percent yield at failure, if that's also data that you're looking for, if that's unique to your own testing processes. So you could essentially find that. As far as establishing it, you could establish one, and again, whole reason why you test, right? You're looking to establish an ideal percent yield when your samples fail. Yes, you know what the failure load is, the load at failure is, or what the deflection at failure is. I'd also like to see what the percent yield is. Software-driven tester will help you do that. The reason I keep kind of bringing that up is because it makes things really easy for you and your operators, so you don't have to guess at anything. So there are inbuilt calculations that will give you this data. Again, inform whatever stage you're in, whether it's R&D or quality or production, you should be able to get all the data you need. Back to you, Laura.
All right, so one more question here. Does the speed of the test affect the test results?
Not really. Again, in most testing applications, what you're looking for is you're trying to simulate what happens in real life, right? So whether it's during the process of filling the container, or whether it's in storage, whether you're stacking 10 high or 15 high, or whether it's in transport, or when it gets to its destination, how, where did it sit before it gets on the shelves, how long does it sit in storage and how much. So you kind of make an educated guess on what a realistic speed of the test. Obviously, it's not a very high rate of speed and it's not too slow. But again, there are industry practices that dictate anywhere from 10 to 12 inches per minute, from 5 inches per minute to 12 inches per minute is fine. The key is consistency. Once you determine what your test procedure is, especially when you're not testing to an established standard set by a testing ASTM or ISO, if you're creating your own internal standard, then you can determine on our 12-ounce bottles, we're testing all of these at 5 inches per minute. On our 20-ounce bottle, we're testing all of them at 15, 12 inches per minute. But consistency is the key. Once you establish a standard, you need to stick to it. It's the only way you can identify any of those outliers or when samples are actually failing. Back to you, Laura.
Okay. All right, we have one last question for you, Moses.
Sure.
What is the largest container we can test?
Okay. So the tester we're using for our demo today is our, I call it our base single column tester. And there are a few options on the different sizes of containers you can test, depending on what that throat depth is and how large your base plate can be. But there are different sizes now where you can test, up to your water fountain jugs. Using a dual column. So again, I did mention, depending on the size of the container, you'd be able to get a little bit more information in the selection of the testing instruments you're going to use. So I know we're using a single column container here, and these samples are relatively smaller, not small, but you can test from these sizes all the way down to much smaller sizes. But if the containers are larger, then you should be looking at larger testers, which are selected not necessarily for the amount of force you can apply, but the space where you can actually accommodate the larger samples you're testing. So if you think of your regular water fountain, you've seen the big jugs that go in the water fountain. Yeah, you can't test those in a dual column because there's enough space to allow for that on the base of the tester. Back to you, Laura.
Awesome. Thank you so much, Moses, for sharing your expertise with us today. And this is all we have. If you have any questions and we didn't have time to answer here, please don't hesitate to send your inquiries to Moses or to info@mecmesin.com. We're excited to see you at future webinars as we continue this journey, learning together. And until then, take care and thank you once again for your participation.
Thanks, everybody.